Hello, this is my final astronomy journal. So, my thought process was I have a lot of notes written and I don't have like my thoughts really expressed in these notes, so I figured I'd just go over a couple from each week and then from there just go into my thoughts and that kind of stuff and like any questions I had about that when I was reading or listening to lectures and that kind of stuff too. So, this is from week one. Um, so we have astronomy the root words are Greek, astro for star, and onomy for the study of stars, obviously, how most sciences work. And it's all about understanding the laws of nature outside of Earth, and it's based on the laws of physics, which I was a little bit confused by at first, but as you kind of go through more of the material, I felt like my question was answered onto why we needed physics for it so badly. Um, I feel like we just need physics because that is the only way we can really use to get knowledge on the stars, and we are currently assuming that physics is what works in space too, which I think is really stupid personally, but it's how I view it. Astronomy is about observable properties of objects in the sky. I think of astronomy as more of like the qualitative of the astronomies, I guess. And astrophysics, which is intrinsic properties of objects in physical nature, as more quantitative because it gets down to the nitty gritty where it's like numbers, like quantitative. And astronomy is obviously qualitative because it's like, oh, the sun is blue mostly, and that kind of stuff. We use a scientific method, so we don't see the stars move from the human eye, and we also have limitations of the technology we use. So not only is like my understanding of that, like we obviously like when it comes to science and that kind of stuff, nothing is for sure. And because of that, the way I view astronomy is like nothing is even more for sure because not only do we have the like hypothesis where and theories where like they can never be proven true but they can only be stronger, you also have a limit of the technology, which I think is like really crazy. I found that really interesting how like we know so much, yet in the first week we talk about how we have a very limited use of technology, and I thought that was really cool. Astronomy is a time machine. This was like my favorite thing ever. And about how we're observing things, about how it was in the past. We're observing the sun from 8 minutes, how it was, which I thought was really cool, so I put that down. Um, we then go into how the speed of light and like how astronomy is an indirect science. We can only observe it indirectly from the light of the object. Unique quality of astronomy is the fact that it's an indirect science and that we can only observe things indirectly and how they were in the past because and like how bright that object is the only way we can observe it. So if it's not that bright, it's kind of hard for my understanding of it. I might be wrong though. Astronomy is a basic science. Basic science are important to us, from my understanding, because while they may not be beneficial immediately, they can, maybe 50 years down the line, you're like, wait a second. What we learned 50 years ago in astronomy could be really relevant right now, and that's really cool. I like that. So we have less rapid insight as a result. But an example which I thought was really cool that you mentioned was the CCD camera, which is in our phones today. I thought that was really cool. It's an observable science. We use scientific notation, and there's really like not much I want to go into about week one, just because week one is more so like the background of everything. But we learned about how the historical views of astronomy and how Greeks wanted to understand nature, and like it's inherent for people to just go and look at the sky and have this interest and be like, what the hell is going on? And I thought that was really cool. I also thought what was really interesting is how in astronomy we go through this like historical time period where we just go back and forth between the geocentric and the heliocentric model. I thought that was really interesting and very, very confusing too. Honestly, I was very confused on why we kept switching, but I just went with it. So in 1572 a supernova appears, causing the questioning of the old view that the heavens are unchanging. So At one point in astronomy, basically what that means is that at one point we were like, hey, this is all really cool, and then the stars explode, and they had like these set laws, and that's just proof that science is, not always right, because we didn't know supernovas existed until, what was that, 1572? So we talked a little bit about Newton, the nature of light, Thomas Young. Wavelengths are very, very important in astronomy, and I do want to get into those for sure, because that is really, really important to us. Wavelengths are different colors because the wavelength of light is different. So visible light is from 400 to 700 nanometers. I don't know what the A means. That's like one question I've always like consistently had is like this A with like this really weird letter on top. All the weird letter stuff, I actually don't know what any of them mean, honestly. So those are like my only questions is like that, and like how we can have an easier way of understanding them without adding like a weird. But then again, some of the lectures, like the letters got messed up, so I'm just like, I don't know. So we have wavelengths and that kind of stuff, and we find out that light is like a wave, and that electric and magnetic fields are waving. And this is like super important to science in general, but also to astronomy, because this allows us to be able to like figure out how, like the colors and that kind of stuff. And that's just like my view of it. It's like you can be like, okay, so now we know blue is like one thing, like it's a it's a hot star, it's so hot it's blue. And red is like it's hot, just not as hot as a blue star. So I think that's really cool. Electric and magnetic fields are waving, and because of that they are two aspects of the same. We also go into spectra and black bodies, which absorb all EM radiation, which it strikes and is heated. Energy is re-emitted. Amount at each wavelength depends on temperature, provides a connection between temperature and energy. Black bodies, I guess, kind of just talks about how you, like, when it gets hotter, it changes color, which is what I was talking about earlier. At least that's my understanding of it and how I view it. I would just say, I'm going to wrap up this stuff now and just say I don't know why we needed the Bohr model for atoms. I didn't understand how that was important to what we were learning, I'll be honest. But I thought everything that was in there was just really super duper neat and that kind of stuff. And it was just like a lot of like little like fun facts to me. And I was just like, wow. And now we are going to week 2. And hopefully it'll be shorter than 8 minutes. You can speed this up too. I hope I'm not talking too fast for if this was speed up, then it's really hard to hear, but astronomy is an indirect science, as we know. We learn about astronomical objects through gravitational waves and the nature of light, which I think is super duper crazy, because that's just, it shouldn't be that way, in my opinion, because science is, like, I feel like we are relying too much on physics and what we know about physics and how they apply to Earth. And this is my beef with physics and science, my beef with physics in general, especially in astronomy, is because of that. And then, as a result, like, if physics was wrong in space, then, like, what's gonna happen? And I just feel like a lot of the stuff, like, we learn things through, like, these very indirect ways that we're like, oh, this is kind of like a loophole, and we're applying to how we know about it in Earth and hoping it applies in space. And I just feel like it's not the same to me. It just doesn't make sense, especially because gravity is a lot weirder in space, as we know. However, in week 2, we kind of talked about how we measure things, especially about the nature of stars. So there are parallaxes, which really confuse me. There's also light years, parsecs, and another astronomical units. Each are very, like, they're niche, they're only used for astronomy. They make sense in astronomy. However, if I was like, yeah, that's less than an astronomical unit away, like, no one's gonna care. However, I do remember off the top of my head that the AU is the distance from the Earth to the Sun, and that's 1 AU. So, woo. So parallax is a way of like measuring like the weird like I don't know how else to describe it. So we talk about apparent magnitude, which is the log scale of the eye's response. So if it's faint, it's a +6. If it's bright, it's a +1, and this is the naked eye limit. And then from there, we also were like astronomers were very creative to reach for all this knowledge, and they're like, all right, well, if a +6 is what we get from the naked eye limit, then like 1 magnitude from the naked eye limit is 2.5 times the real brightness. So 1 to 6 is 100 times difference. Magnitudes can also be negative. For example, the sun is -25. That's confusing. Why is the sun -25? It's just that bright, I guess. I think what also really confused me in this bit was that I feel like when you go brighter, you think more positive, but they went more negative. So I was like a little bit confused by that at first, but I thought it was like fine afterwards. It was created by a Greek astronomer, so it's kind of funky. I literally wrote that in my notes, so I just wanted to read it. From there, apparent magnitude is not real brightness. Apparent brightness decreases because of the inverse square law. I'm not sure. Like, the inverse square law confuses me a little bit. Like, I understand that we don't see the real brightness of anything ever, but that's also because we look at it in the past and all this other stuff. Like, the one thing that bothers me consistently is that astronomy is a time machine, and because of that, it confuses me because I'm like, we look at these things and they are like how many years in the past, and no one like it gets mentioned once and then never again, and I'm just like, what the hell? It's very upsetting. So we need to be able to compare real brightness, so correct for distances, development then of absolute magnitude. Absolute magnitude is apparent magnitude of an object would have if it were at 10 parsecs. It's difficult to obtain since we need distance of objects, but it also supplies that formula. This is again my view of astronomers reaching for knowledge. They, like, I guess my thoughts are it's really insane how astronomers like reached for all of this. They were like, we are going to get this and we are going to get this now. And they just kept being like, well, if we can't do it like this, then we can try this. And like, you can tell the dedication and the mental strength to do this because they're like, okay, well, it would have if it were at 10 parsecs. They invented parsecs, first of all. So, like, I feel like astronomy is like a science where you can just invent things very frequently in a way. Like parsecs and that kind of stuff. Luminosity is also related to absolute magnitude, which is the physical brightness of the source. Depends on the radius of the star, size of the star. It tells you how many photons are leaving the surface. Photons are pretty important from my understanding in this class. Luminosity is also the energy produced in a star. So I am trying to like go through each week, but I can go on a whole tangent right now about luminosity, so I'm going to try and save that for later. We also have categories of surface temperature, which go O, B, A, F, G, K, M. I thought that was pretty important for some reason. I don't know why. We also have Wien's law, which is about involves stellar temperatures. Use a photometer to measure light intensity and filter to measure intensity at different bands. I don't know what that means, genuinely. So I'm a little bit confused on Wien's law. We have the HR diagram, which I luckily did not have nightmares about, but I did fall asleep thinking about it a couple times, which was terrifying. We use a diagram above for stars. Black dots are the surface temperatures of stars. So the x-axis is surface temperature, while the y-axis is the luminosity and absolute magnitude because they have a correlation together and that kind of stuff. So there's that. And then from there, we can kind of see, like, where these different things are, like, where all the white dwarfs are. The main sequence, which goes in the middle, and then the supergiants and the regular giants. And that's really cool that the HR diagram shows all of this. And I just think it's really neat. The HR diagram was, like, my favorite part, honestly. We learned about Different types of, so main sequence holds 90% of the stars in solar neighborhood. They're dwarf stars. O-type stars are the rarest, which are the white dwarfs, and then M-type stars are the most common, which is just like the stars in the main sequence. Most main sequence stars are like the sun, which I thought was really interesting because I feel like the universe would be a little bit more original. Apparently not. Giants are in the cool part of the HR diagram by Boltzmann's law. If something is cold, that means it has less energy. And then by default, if something is warm, it has more energy. But these giants are very bright. Like, their surface temperature is not good, but they're bright. So they're up here. And I believe, yeah, they're like right here if this was like the square of the HR diagram. And it's just really cool to me that they are so huge because they're like, they must be huge because they're so bright and they don't make that much energy because they're cold. And I just think that's like absolutely insane. Like, that is absolutely insane. I don't know how else to describe it. Supergiants make up 1% of all stars and are even bigger than giants, and then white dwarfs are 9% of stars. We also have binary stars, which are stars that orbit each other. I can't think of an example like this, but we also have like different types of binaries, which I'm not going to really go into. However, the more massive a star, the more luminous. This is Kepler and Newton's laws. Or, no, that's the mass-luminosity relationship, so... And then on top of that, Kepler and Newton's laws, you can combine those together to measure stellar mass. Newton's laws are like the basic laws of physics. And then Kepler's law, I know I have somewhere. Kepler's laws, I'll read those to you real fast. So the orbit of a planet around the sun is an ellipse with the sun of one at focus. Law of equal areas, a line joining a planet and the sun sweeps out an equal, and then the square, this was added later, the square of the planet's sidereal period is proportional to the cube. I honestly don't understand Kepler's laws. I do not. Like, I read this and I typed it and I was like, I'm so confused, I'm just gonna type it. But that's about it for the rest of week 2. It just kind of goes about how stars move, everything in the universe moves, and that's about it. So let's go to week 3. Oh yeah, week 3, this is really sad. Week 3 was about the sun, and apparently my document didn't save when I went to go take like 10 different notes on the sun. So I'm just gonna go on a short tangent without the help of my computer to go through things. Unless there's another week 3 journal note, there is not. That is so sad. And I don't think we had a week 4, so then week 5 is after. But the sun is basically, it just goes into this whole tangent about the sun, the future of the sun, which is like what I found the most interesting, because astronomy, like for me, as a psychology student, doesn't really mean that much to me, but as this class like continued on, it slowly got like more and more interesting, and I was like, oh, I like learning this stuff. It's just, I don't know if I could ever be a professional in it. And the sun was one of those things where like the fate of the sun and how it's like, yeah, it might blow up, might not. The sun has different, like an atmosphere to it as well, which I thought was really cool. And the sun, like, we can't see after a certain point in the sun. And that's really creepy to me because that's like right there. It's down the street in the solar neighborhood, I guess. So I didn't really like that. And then it's so hot it makes it makes hydrogen, and then it goes to helium, and then it's gonna explode because it's not gonna be able to produce the next thing on the periodic table. Which, fun fact about the history of the stars, is one supernova kept making these things and then it blew up, and then that's how we got all the stuff in the periodic table, and I think that's really cool, and that's something we learned later in cosmology, so. Anyways, next we go to star formation. So basically, a star is formed through giant molecular clouds, which are very cold, dense gas/dust clouds. They're dense in an astronomical sense and not an Earth sense. So basically, what this means is that, like, Earth, like, this is dense, you know, like, I can't go through it. However, like, when it comes to stuff in space, like, it's not gonna be as dense because, like, it's space and these are gas and dust clouds. So automatically I'm thinking gas, like I can put my hand through it. And dust, I can sweep dust away. So that's what they mean by that, is my way of thinking about it. Heavy elements are things that are heavier than hydrogen, and that is it. So basically everything that is heavier than hydrogen is a heavy element now, or metal. Thought that was stupid. GMCs are important because they are what stars form from, and these GMCs are giant molecular clouds, and they form by cloud-to-cloud collision, so two clouds, like, or supernova explosions, and that's where star formation begins, and that's why GMCs are super duper 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 important to the world, because if we didn't have GMCs, then we wouldn't have the Earth and the stars. So, alright, I guess, yeah, that makes sense. So cloud collapse are cold, dense clouds start to collapse gravitationally. So it needs to be cold so it'll collapse. So that's like a very important part, is the fact that it is cold. Gravity will collapse in, and then after so many years, mass builds to roughly one mass of the sun. The core heats through the release of gravitation potential energy, and then radiation pressure stops accretion, and then it'll create a protostar. And basically this just goes down, and a protostar is a pre-main sequence star which contracts due to gravity. So it's not yet on the main sequence. It's like still kind of like, it's still a baby star. It's not yet really formed yet, because they need to collapse and form a dense core together. And then from there, it will just kind of heat. This core will heat through the release of gravity of potential energy over and over in time. And so 3/4 fusion starts, radiation pressure blows off material, newly formed star. So those are like our steps. Is we have the GMC starts to collapses and forms a dense core, fusion starts, radiation pressure blows off material, and then we have newly born star. And those are the 5 steps. They're very important. They're very, very important. Mass is the most important property of stars, and I think that's because we use mass so much. I didn't understand why. I felt like luminosity would be more important because it's like the brightness of the star, and luminosity has a direct relationship with like surface temperature and that kind of stuff. So I always viewed like those to be more important, but according to this, like the star's mass places it on the specific part of the HR diagram. If mass is too low, the core doesn't heat up enough to start fusion, which will make a brown dwarf, which is slightly more massive than Jupiter. I thought that was pretty neat. And then, yeah. So we have a mass limit specifically for main sequence stars, so they can only get so big, is what this means. If they're too low, the core will never heat up high enough for fusion reactions to initiate, and these fusion reactions need to initiate because that's what makes the helium and hydrogen, or hydrogen and then to helium and then to oxygen and carbon and all that kind of stuff. So we kind of need that. Also, when stars are born, they typically are formed in star clusters. So stars can be formed in clusters because the stars are big ionization cells / supernovae, compressed gas leading to star formation. Strings of star clusters of increasing age in large star forming regions. By plotting stars in cluster can determine age more later. That was just a weird tangent. I'm gonna ignore that one. We have nebulas, which can happen after stars form. Nebulas can go by different names, and because they're made of ionized hydrogen, we call them HII regions for singly ionized hydrogen. They basically are these hot O and B stars. They have a lot of ultraviolet radiation, and they ionize the surrounding nebula. Recombining makes a nebula grow, which is an emission nebula. Nebulas just seem like this kind of like really cool phenomenon that happened, but like they don't actually mean anything in the grand scheme of things. It's kind of like, wow, that's cool. It's like this. Like, yeah, we know it happens now. That's cool, but like it doesn't do anything really important that we know of yet, from my understanding. So, the bigger the star, the more fuel it's going to use. So, the more massive ones, they use their fuel faster, and the least massive ones live the longest. I feel like that's pretty self-explanatory. And then giant molecular clouds are rotating around the galaxy, and as it collapses, it rotates, and that's why the star rotates. So that's pretty important because it explains like the phenomenon of like, well, why are we rotating? Why are stars rotating? It's because the GMCs are rotating too. And that is week 5. So let's move on to week 6. So this is travels on the HR topics, travels on the HR diagram. So it's very important to us. Like this is like the most important thing in astronomy is this diagram because it kind of categorizes everything from when it comes to stars specifically, and stars are really important as we know. So we have the O-type stars, the M-type stars, the main sequence. We have supergiants, giants, and white dwarfs. So low temp but big are supergiants, hot but faint are white dwarfs, and giants. I didn't write that down, so whoops. We can only measure surface temperature. We can never measure we measure the surface temperature of the star by determining the color of the star, which we already went through. The main sequence, they're fusing hydrogen into helium in their cores. Most of a star's life is spent on the main sequence. So this is like interphase in biology. Like interphase, you spend 90% of your life in the cells, so you can compare it like that as well. The most luminous, the more massive, but also the faster it dies because it needs more energy. The higher the mass, the higher the gravity, and it'll squeeze the core of the star. The higher the temperature, the faster the fusion rate, more massive, and therefore the faster it'll burn its fuel. When it has low mass, it's slower, it'll consume it slowly, it'll consume its fuel and will spend 1 trillion years on the main sequence. So that's about that when it comes to like main sequence stars, is like they spend a lot of their time there. And then like the more luminous, the more massive, but the faster it dies and that kind of stuff too. Hydrogen conversion. So this basically goes into like how some stars, so what I understand with this kind of stuff, and I think this is really important, is some stars cannot fuse after helium. So when hydrogen is completely converted to helium, it just stops fusion. But in some stars, fusion will continue because they have enough energy to. However, some just don't, and that is the case where it stops at helium. So this is a hydrogen conversion. No radiation pressure to support the gravitational collapse. So gravity is like pushing in on this core at the same time, and the fusion was kind of keeping gravity away in a way. And then this new energy source is larger than the core. Since it's outside of the core, when a gas expands, it cools. And this is all about the hydrogen conversion, and red giants is like they keep making stuff, but like it's you gave a really good analogy in one of the lectures about like how if it gets really hot, the air in the tire, and then whenever you come it out and you get burns, that kind of stuff. So that was something that I remembered. We also have helium core flashes, which are when hydrogen requires 10 to 20 million degrees of fusion. Core heats up to 100 million degrees to cause helium fusion. We're using more material when we're fusing helium. We need 3 helium to form 1 carbon, and helium fuses into nitrogen, carbon, and oxygen. In ordinary gas, contraction leads to heating, leading to expansion, leading to cooling, a safety value. Core contracts so much to heat up, it squeezes electrons together, and core becomes degenerate. Degenerate is not a good word. Therefore, degenerate gas does not act like ordinary gas. It has no safety value, so it won't just stop. So core flashes in seconds explosively, and degeneracy is lifted. So degeneracy, from my understanding, is like if it's not degenerate, I guess is the best way to explain it, first off, is like whenever the gas goes out, it cools off. When it's degenerate, it doesn't do that. That is my understanding of it. I could be completely wrong, but that's my view of it. We have 2 types of clusters. We have open clusters and globular clusters. Open clusters are younger, and globular are old, outside but orbiting galaxies. They are hundreds of thousands of stars born simultaneously, and they kind of like stay together. Open clusters eventually drift apart. Stars also go through phases, by the way. So obviously blue is hot, red is cold, and that's not the same, but it's in science terms, so therefore it makes sense. And then that's about like the most I want to go on in here. So we're gonna go to week 7 now. I feel like I'm doing good on time. I'm going over how much material. Okay. So this is about how stars die and their endpoints, like stellar deaths and endpoints. So low mass stars, like the sun, live about 10 billion years on the main sequence, and their reactions stop at core uses up helium, carbon, and oxygen. Left reaction stops, so it stops there. It stops at those three. And you need, basically, that's because you need higher temperature to fuse heavier elements than that kind of stuff, so they don't have enough temperature. The core collapses because of gravity, and shells of helium and hydrogen will ignite. This is for low mass stars, by the way. And then it'll become an envelope expands and becomes an acytomic giant branch star, AGB. It's very bright and enormous. Pulsations in core rate blow away bloated atmosphere, or atmosphere cools. Shell of the atmosphere is ejected and hot core exposed, ionizing gas causing it to glow. And then a planetary nebula is formed. It expands to low density, merged into interstellar medium, and basically it just makes cool light. Planetary nebula matter is then returned to the interstellar medium. It is enriched. Carbon and oxygen core is never ignited. It's a leftover ember white dwarf. Degenerate electrons, size of the Earth. Just cools thermally. It has a very high density, though, these white dwarfs. And they can be more massive than 1.4. Oh, cannot be more massive than 1.4. 1.4 what? I don't know. And that's because of something called the Trans-Saccharine limit. And that is the life cycle of a low mass star, basically. Is after 10 million years, it expands to a red giant. Outer atmosphere blows off to become a planetary nebula. So that's when the gas is getting cooler, and then it's burned out and left as a white dwarf. When it comes to high mass stars that are 5 to 50 times the mass of the sun, they have a very short lifespan. They last about 1 million years. They create elements through iron. They have an onion skin because they have multiple shells fusing outside the core. So they have multiple things just going on. Like, they, again, also create up to iron. That is a very big deal. Like, iron is that's like 16 or something from my understanding of the periodic table of elements. So that's pretty important. And that's just like for me, who isn't good with numbers and sees all these big numbers and doesn't really feel like, shit, that's big, or like that's hot. For me, this is like my holy cow moment. Like, we are making iron, so it must be hot. But then the core is the size of the Earth. They're fusing materials faster and faster. Oh, that's not the right thing. So they have the onion skin. They expand into a red supergiant. They're very bright, but also very large, and then they will explode as a supernova and leave behind neutron stars or black holes, which I will talk about more when we get to the black hole week. So we also have different types of supernovas as well. And these types of supernovas are type 1 and type 2. Type 1 begins as a white dwarf if in binary mass transfer can take place, and when the white dwarf exceeds the Chan-Drake-Scar limit, it explodes, and that is that. Type 2 supernovas are when the core fuses into iron, the core shuts down, and it collapses very fast. This is catastrophic. Neutrinos form but cannot escape tremendous pressures. Material is falling into core, bounces back out, burning, blasting everything in its way. It's super hot, and it's just producing a lot of photons and extremely bright. I'm shining all stars in galaxy for briefly. So that's a type 2 supernova. They're a lot more intense compared to a type 1. And then there's regular nova and supernova, which are so a nova is a non-disruptive explosion of material falling onto a white dwarf from the accretion disk. I don't know. Actually, I'm just gonna stop that. There are these things called pulsars, which are the end states, one of the end states of a supernova. So a pulsar is a collapsed core of a high mass star / supernova. It is 10 kilometers in diameter and extremely high density. Some are magnetized for some reason. I don't really know why. That's like a question I had, is like, why would they be magnetized? But they spin really fast, which is pretty funny. Um, Beams of particles squirted from the magnetic axis towards us see regular pulses. We can get to hundreds of pulses per second. Jocelyn Bell discovered these, which I thought was pretty cool because it's a woman in science and we don't see those often. End states, we get to black holes. So black holes are very... they're not good. Just a little tangent about them for now. We don't know anything about the interior because physics don't work in it. Black holes are black because their gravitational fields are so intense that nothing can escape them, even light. That is terrifying. They are also 3 times mass of the sun, 2 billions of times the mass of the sun. Anyways, so this is my favorite little sentence, is we are star stuff, because high mass stars, they're really, really important in astronomy, and this is because they create iron, and this is why I keep talking about iron and being like, that's crazy, because they created iron. And because of that, they like created all these heavier elements. They basically filled up the periodic table. They exploded and dispersed these elements to next generation of stars. So the magnesium in our blood and the calcium in our bones is like from the stars, I guess. And this makes us star stuff, which is really fun. And I think that's really cool. And that's my favorite part of astronomy, is the fact that we are star stuff, and I get to say that now. And I was so excited writing that. I don't think we have a week 8, so I'm gonna go straight into week 9. So this is about distances in the Milky Way. So basically, before we even start, there is a historical like bit to this. The first thing is, this is week 9, by the way. There is the Curtis-Shapley debate, which is how big is the galaxy and what is the nature of a spiral nebula? For about 50 years, astronomers made surveys of the night sky. They noticed these nebula that were very different compared to what they normally see, which are spiral and not regular nebula. So the debate occurs in 1920 in DC. These are not very common in astronomy. Both views are partly correct and partly wrong. This debate did not resolve any issues. That is it. This debate means nothing. Like, this debate is important to me as a student because it is so stupid. That is that. And it does actually mean a lot, because so Curtis, his view is that the galaxy is small, Spiral Nebula is outside the galaxy, Shapley is our galaxy is big, and Spiral Nebula is part of our nebula. It turns out that our galaxy is... our galaxy, measuring the shape of our galaxy is hard. We're inside. We're stuck where we are, so it's kind of hard to be like, is the galaxy big or not? Because we're in the Milky Way, and we don't know. So, basically, the Milky Way is a faint band of stars that circles the sky. We've known the Milky Way is composed of stars since Galileo. Our early observations, so William Herschel in Britain in the 1780s assumed stars of uniform brightness, and distributed it evenly. So basically, he was going on this whole tangent about the heavens are perfect, which we talked about earlier, and then the supernova would occur later. So Herschel's results are, as a result, because of this, spiral nebula are probably other galaxies, and we are at the center of the galaxy because he's self-centered. And interstellar extinction is just basically like blue light is all scattered. We didn't know about extinction prior to the 1900s, so we really ran with Herschel's results, I guess. I don't know. But he was only absorbing 5% of the galaxy, so he had a very like distorted view of interstellar extinction and just everything in between. So Herschel tried his best, but I feel bad for Herschel now. I feel bad for calling him stupid. So we have, let's see. Oh, standard candles. These are really, I like these a lot. So these are objects with a known interesting luminosity. So if something is a standard candle, we automatically are like, oh, we know the luminosity of that. It is the same wherever the object is, and luminosity is known fairly accurate. Comparing absolute and apparent magnitudes gives distance. How we extend that cosmic distance ladder scale for larger types. So basically, this happens, and we learn about dust, and how dust, I don't know, actually. I don't know what this means in my notes, I'll be so honest. I'm sorry for talking about dust for no reason. But we talk about Cepheid variable stars. These stars kind of confused me, but it just seems like they're very important because they help us create more distances. And because these were one of those stars where they were very high in luminosity and found in globular clusters. So because of the period, we get the luminosity, and by the luminosity, we can get the distance. So I think that's why they're important. So the current picture, which is just how we view things today, our galaxy is 50k PC in diameter. It contains hundreds of millions of stars. There are other galaxies behind ours. The universe is really, really big, basically. There's hundreds of billions of galaxies. It's massive. Our galaxy, so we have 4 different things that are pretty important. We have the disk, where all the blue stars and ISM are found. The bulge, which is a spherical region near the galaxy's center. It has old stars as well. The nucleus, which is just like in biology, the center. And the halo is like the surrounding the disk and bulge, which is also old stars. So the halo is like the very outskirts. So I would say it goes nucleus, bulge, disk, halo, and ka-chow. So the disk has lots of gas. Optical telescopes aren't being very useful because they're being absorbed by the interstellar medium. We also have these spiral arms, which are pretty interesting. These spiral arms, most young stars, blue stars in the galaxy, are in the spiral arms. So the arms are the sites of ongoing star formation. So these spiral arms have star formation going on, and they also have these blue stars, which are young stars. These are formed in the spiral arms. These clouds are found in the spiral arms, therefore they're massive young bright stars, and they also die rapidly, are these young blue stars. They are low mass, long-lived these bright blue stars highlight the arms and make them easier to see. Most stars are low mass, long-lived stars between the arms, but some can also just die rapidly. We have population 1 and 2 stars. Population 1 stars are like the sun. Population 2 are older stars. We don't know where the arms come from. So week 9 on is basically a lot of open-ended questions in astronomy, and I want to take time to kind of be like, this is what I think and my personal view. So I'm sorry in advance. So where do the arms come from? Why are the arms winding? We don't see this, so don't see winding, so arms aren't forming from orbiting stars. We also have ripples. Oh yeah, and there's also dark matter. So dark matter, we really know nothing about besides that over 90% of the mass of the galaxy is composed of it. From everywhere we can measure its gravitational influence, the universe is full of it. We don't know exactly what it is. We have some candidates, which are black holes, because we don't see them, but they do have mass. And if there be enough black holes to cause dark matter, we'd notice. Brown dwarfs, just simply no. Neutrinos, there's lots and lots and lots of neutrinos, but they aren't massive enough. We think it may be something with subatomic particles like WIMPs or Higgs particles. My opinion, I guess, on dark matter is that it's really interesting because it has no detectable electromagnetic emission, so we can't like find it like that, and like we can't send stuff in it because it's just not gonna come out. Like it's gonna get absorbed. It is found everywhere. So, or wait, that was a black hole, but dark matter also has no electromagnetic emission. So, I think that's also why it makes it a good candidate for like why it could be a black hole and that kind of stuff. But I don't think it gives the answer. I think it's just kind of like it's like the space that fills up the space, is how I view it. And that's like my view of dark matter. I don't know what it could be. I'm assuming it's just really, really tiny particles. Or like really, really tiny atoms, maybe like helium and that kind of stuff. Oh wait, no, it can't be helium because it has no detectable electromagnetic emission. Okay. I don't know. But that's pretty crazy. We can weigh the galaxy of use of orbits of stars to measure mass of galaxy. We use Newton's laws of gravity for this. And that's about all I want to touch on week 9. I also just 10. So this is galaxies and clusters. So we go through our types of galaxies. So we have spiral galaxies and then we have elliptical galaxies. So we're going to first go into spiral. So spiral have like these different types, but they have a nuclear bulge in the center. They have spiral arms, which contain the star formation and the interstellar medium. They have knots of glowing star cluster, or of interstellar clouds, gas and dust, and they're predominantly blue. That is them. Their properties, they have lots of gas and dust, they have ongoing star formation, there are hundreds of thousands of light years in diameters, and hundreds of billions of stars. We are currently a spiral galaxy. Hubble thought that elliptical galaxies turn into spiral ones, but we are not sure of that today. And basically, astronomy had a question of, can we put galaxies in bends? Are they unique? We can't put them into bends. We have different types of spirals, which are broad spirals, but elliptical galaxies, I won't go into those. They do not have spiral arms. They're either like kind of circular or oval. The classification is based on how round or oval they are. They may look different at every angle, so by default they can get classified differently. That really upset me there, because it's like, hey, we're looking at Andromeda. Andromeda is a spiral galaxy, I know that, but I'm gonna pretend it's elliptical. But it's like stupid, because I feel like if you're looking at it from one angle and you know it's Andromeda, and then you look at it from another angle, like, it just doesn't make sense to me, because I know it's from like the way you're looking at it, but I don't like that. I think it needs to have one set thing, not like 3 different ones based on what angle you're looking at it from. But they have no current star formation. There's little gas and dust, at least cool gas. They're large in size and number of stars, and they're reddish and made up of low mass, long-lived stars. They range from the smallest to largest galaxies, ellipticals do, and we don't know how they're really created. So this goes into this whole theory of like, well, what happens when 2 spiral galaxies like bump into each other? And that's really cool. We also do have irregular galaxies, which are just kind of like the redheaded stepchild, and I can say that because I am one, of the bends. There's no spiral structure or disk. It's not elliptical in shape. It has very unusual shapes. It just doesn't fit in any other category. So they're like, irregular galaxies. And then we have clusters of galaxies, so we have different cluster types too. So galaxies are grouped in clusters, members are gravitationally bound, clusters can also be grouped into superclusters, which contain dozens of clusters. And then there's going to be voids between superclusters, which are vast empty regions, galaxy clusters concentrated in sheets around voids, like soap bubbles. I don't understand why it's like soap bubbles, I will be honest. I was really confused whenever we went through that part in the lecture, and then you showed a picture of soap bubbles. That like kind of confused me, and I kind of just was like, okay. Laws of nature work to make the structures the way that they are. We have cluster types, so you can be poor or rich. Our local group is a poor cluster because we only have 30 galaxies in our cluster. Andromeda is the closest galaxy next to us. Rich clusters, which an example are Virgo, which is 50 million light years away, but it has roughly 1,000 galaxies over a large area. So rich clusters have mostly elliptical galaxies, while poor clusters have more spiral, which is like a little weird thing that I feel like should be explained by something. I don't know what the explanation behind it is. I don't know if it's because spiral are still doing star formation and elliptical are not. I don't know if that like has a relation to why rich clusters are mostly have elliptical galaxies compared to poor clusters having spiral. I don't understand that. That is something that makes me interested in like a question that I want to answer. So the open question is collision in clusters, and like galaxies do collide. Stars don't interact, but the gas and clouds do. And collisions can cause star formation and galaxy mergers, which is what we were talking about. Also, there's galactic cannibalism, which is really messed up. Big galaxies can absorb smaller ones. Woo! That's my favorite thing ever in this whole thing. Galactic cannibalism. Maybe I'll write my paper on that. Finally, so we have some open-ended questions. How do galaxies form? We are trying to figure out if spirals form from top down or bottom up, which is like how. So top down, glass clouds collapse and rotate and forms a pancake. That's the top down method. Bottom up, which I believe is what everyone thinks it is. Our spiral galaxies made up of little clumps of stars and dust that came together to form another. Recent observations are finding very large galaxies, but very early in the universe. Galaxies are forming bigger and faster than we thought we could. Ellipticals, we have no clue how they form yet. We're kind of just, I think, from my view of it, everyone thinks it's spiral collision, like two spiral galaxies, like, but no one knows for sure, and I'm guessing the best thing that's gonna happen is one day we're going to eventually collide with Andromeda, and we'll become an elliptical galaxy, and that's what I'm waiting for, personally, and then we'll get our answer, and I probably want to be alive for it, but it's fine. We then talk about redshift for a bit, and this basically means Hubble observed through a telescope these spectral lines that shifted to red. Redshift basically means that they're receding from us, and they can be linked, the like shift, that redness can be linked to the velocity of galaxies moving away from us. So redshift is recessional velocity, and that's like, I don't think it's that important, redshift. I understand why it could be. It didn't really get talked about much for me. Okay, so we're talking about black holes, quasars, and active galaxies now. I'm just gonna skip, like, quasars. I'm gonna go on their tangent now, because quasars really confused me whenever we were learning about them. I don't know what they do. I just know they're seen in the radio. They're extremely powerful at all wavelengths. So I don't know if this is like something that you only see on like wavelengths or what. Some have jets, but also black holes have jets. So I don't know if how a quasar is related to a black hole. I don't know that. And it doesn't really, like, I just know they're a subclass of active galactic nuclei, which is AGN. AGN includes Cepheid galaxies, BL, Lyrae objects, quasars, which are giant ellipticals. I don't know what that means. And radio galaxies. Basically, I'm just going to talk about black holes, because the quasar stuff, again, as I just mentioned, like, really confused me, and I didn't understand it, and I don't know how to further my understanding of it. I might just be stupid and not get it, and I don't know. But black holes I really understood. So some evidence for black holes is indirectly, gravitationally, from binary stars for celestized ones, or stars orbiting supermassive ones in galaxies. We usually can measure the mass, but we cannot see it electromagnetically, so therefore it must be a black hole. From the matter, in an accretion disk, we see X-ray flickering, which is kind of like, oh, then there must be something going on. So this is like these little indirect evidences, but they are very important. Supermassive black holes are built up from the smaller black holes in galaxies. The question is, what comes first, a galaxy or supernova? Or was a large black hole in place that attracted gas and dust to form the galaxy it surrounds? We don't know yet. It's an active area of research. So we don't know what came first. It's like the chicken or the egg, but we don't know the answer yet, and we just need to keep looking back in the past of the time machine that is astronomy, I guess. And then finally, black holes, they are in the center of all galaxies. The center is called, so they're stellar size one products of supernova. There are supermassive black holes and then regular black holes. It's a collapsing, there is, nothing can escape. Nothing can escape. We have a supermassive black hole in the middle of our galaxy, which is great. Black holes are 3D objects. There's an accretion disk. There's an event horizon, and they have mass, electric charge, and angular momentum. The electric charge is really interesting, because why does it have electric charge? I think he might have explained that, but I never remembered and wrote it down. So why are they electrically charged? Is it because of the stuff they're absorbing, or like what? Okay. Week 13 and then week 14. So week 13 was about the Big Bang and matter, so we go through a whole little tangent. Assumptions in the past. The universe is infinitely big, the universe is infinitely old, and the universe is uniform. However, Olber's paradox is a simple question. Why is the sky dark at night? Everything is the same for a long way in all directions. We have these assumptions in the past. However, this is a paradox, and this is because if the universe is infinitely large and uniform, why is the night sky not bright? Every sight line will eventually hit a star. They don't. And the answer is, then, because of this paradox, the universe cannot be infinitely large or big. So the universe is isotropic and homogeneous. Isotropic means the universe is the same in all directions, no preferred direction, and homogeneous means at the larger scales the universe is uniform, pretty much the same everywhere, same physical concepts apply. We are not in a special place. We are like, if this was the Milky Way and this was the black hole, my ring, we are like over here. we're not special. So, um, and then we have evidence for the Big Bang, which is basically when we roll back time, we have a high energy radium field. As the universe expands, radiation cools. Radiation should permeate entire universe even today. And there's also cosmic microwave background radiation, which is really neat. We have a whole history about that. These guys at Bell Labs were basically looking through and they were like, this is isotropic and smooth, and it's consistent with the Big Bang, but not steady state. But this whole week was just basically us going over the Big Bang timeline and the age of the universe. So we figure out, because of Hubble's constants, 1 helium is roughly an age, that the universe is 13.74 billion years old. The energy budget of the universe, 73% goes to dark energy. We don't know what that is yet. 23% goes to dark matter. Again, we don't know what that is. 0.4 goes to stars and stuff that we see, which is really creepy. And 3.6 goes to intergalactic gas. I'm not going to go too much on this. And I'm just going to skip into week 14, which is the fate of the universe. So the fate of the universe is horrible. Everything's going to eventually die. Life in the universe, lots of planets, organic molecules, and amino acids everywhere. Oh yeah, this is us, like, UFOs. However, universe is expanding. Will it expand forever, or will it eventually collapse? Depends on matter. So matter gets to decide if we live or not. If average density of matter is low, the universe will expand forever. This means the universe is then unbound. If there is enough matter, gravity can stop expansion and will collapse. That means the universe is bound. So there's like 2 different things. So we can be bound and closed or unbound and open. And in those, there's like different ways we look, I guess, in space. So bound and closed, it's spherical and positive curvature. Unbound and open, space is hyperbolic, negative curvature, or space is flat or no curvature. We also have dark energy. Universe is expanding faster than expected, and we believe this is because of dark energy, because of the Big Bang. So the universe was expanding faster. Something is causing expansion to accelerate. Related to what caused inflation right after the Big Bang, we call this phenomenon dark energy. And we are still trying to figure out what dark energy is. So my thing, I guess, is dark energy is probably something on the periodic table. I'm assuming, the periodic table of elements, we haven't discovered everything on there, and that's my assumption with it, is it's just something that's going to eventually be on the periodic table like 20 years from now. And then finally, I'll end off with the fate of the universe. The universe becomes cold and dark, eventually, because space is being pulled apart. And the sea of atomic particles is also getting pulled apart. Earth is gonna die from the sun, or from us, or from a planetary nebula, or the Milky Way colliding in with the Andromeda Galaxy. And yeah, so I guess the last thing I'm gonna do is just kind of like go over my final thoughts and that kind of stuff. This class was really interesting for me because I felt like I learned a lot. Like, I know it sounded like I was just rereading what we learned from this, but it's because I've never taken an astronomy class before in my life. So all of this was like super new to me, super interesting, and just really crazy. So a lot of it, I was just kind of like, for a majority of this class, like, it was just me taking it in and being like, wow. And like, I did have parts where I was confused with like, why, like, some questions of like, why do we rely on physics so much in astronomy, and like, how do we know how far back we're looking in time if astronomy is a time machine? Like, these are some questions I have, but for me, it's like, I feel like those questions are irrelevant in the grand scheme of things because we have bigger things to worry about, like the open-ended questions that astronomers, professionals in the science, are still trying to figure out. So, but I'm gonna leave off with some final questions, I guess, and just like an overall like summary of everything, which I thought was really interesting. I thought astronomy being a time machine was interesting. I like the luminosity relationship to distance and that kind of stuff, and like the color. It was just really cool learning about how like stars form and die, and like learning about the beginning of the universe, because like for the last 2 weeks we kind of just went over like history stuff, and I really like those units the most, but that's just because I'm a history nerd. So learning about the Big Bang and being like, yeah, this is what happened to create us and like how we're star stuff, woo, and all that kind of stuff. So I just thought that was really cool. But I think I'm gonna leave it off here, I guess. Thank you for letting us take this class. It was really cool. I really enjoyed what I learned. I hope this is good. Woo! And thank you. I hope you have a great rest of your day, and I'm sorry you had to sit through me go on a tangent for an hour, but bye!